So today it is a just an introduction class. So I will introduce two different kind of dual concept, duality of function. One that we had already discussed during function, convex function, that was conjugate function, and also we need to recall few concept of duality from convex set as well. So those two dual convex set were what? In case of cone, like one was a dual cone and another one was polar cone. That means if you are having any set, or whether that set is a convex or non-convex, you don't have to worry about that. But if you are able to, you are finding dual cone or polar cone of that given set, then definitely that polar cone happens or dual cone happens to be a convex cone. So and if you apply twice that operation again, then it is just reverting back the original state. So that's where polar cone, dual cone, all those happens to be a dual operation. Or simply you can say that those are part of duality. Similarly, conjugate function is also part of duality, because if you do conjugate twice, then you will get back your original function. So conjugate function, conjugate operation is also a dual operation. In a similar fashion, also you can say that transport operation, transpose. If you do transpose of a matrix, then that one is also a dual operation. Why? Because double transpose of a matrix happens to be the original matrix. So all those are duality means simply that you, when you apply twice a operation and you get back your original one, then it simply says that that operation is a dual operation. So I'm coming to outline of my today's lecture. So first I would like to discuss about the duality concept from that is set and from function that we had already covered in the first modules. And after that I will introduce a new kind of duality concept. Till now we haven't covered this concept. We are calling it a Lagrange duality, and it is very much interesting and find a lot of application in solving optimization problem, this Lagrange duality. And it is totally different other than what conjugate function approach we had already seen that. So it is totally different. That is directly giving an algorithmic approach to solve a optimization problem. Also, when we will discuss KKT condition, that one is also based on Lagrange duality concept. And I will talk at the last. I will talk few example of that is based on Lagrange duality, and directly in this example, you will see that easily you will get the solution directly in dual form. You can directly see the solution of the problem easily. So that kind of pattern we can see that. So coming to first part of this lecture, duality, that one is coming from sets and function. So one example here I have already taken a dual cone. That means we had already discussed during set convex set part that if you consider a cone C, suppose C is a cone, or simply you can say that C is a set in Euclidean space Rn. Then how we can define polar cone? Polar cone we can define it is a collection of all the direction in such a way. If you define a hyperplane A transpose x equal to 0 in such a way that your given set C, it will be in the positive half space. That means if you first define a hyperplane A transpose x equal to 0, okay. So it always, this hyperplane always define a define two kind of half space. One half space that we are calling it upper half space, that we denote it by h plus. H plus is collection of all the points such that dot product of A with x happens to be greater than or equal to 0, upper half space. You know the definition, I don't have to recall much. And another half space would be lower half space. So what is happening in the sense of dual cone is that it is a collection. Dual cone is actually collection of all direction in such a way you can observe that every point of the given set happens to be in the upper half space. That means mm, this is the given set. In geometry, you can see it like this way. This is the given set C, and you can see that this set is not a convex set even. So don't worry about that. So what you do, best way to find a dual cone is that just first anyhow come to know extreme direction. That means the direction which are touching the given set, in extreme way. So there are two extreme directions. There is one extreme direction is this one. Okay, it is touching the set here. Call it D1. There is one more extreme direction. This one. Call it D2. Now you need to construct dual cone of this given set. So how you can construct? So if you take any, suppose if you take any direction, call it A, and define a hyperplane A transpose X equal to 0. So this would be hyperplane. By considering A as a normal vector, you define a hyperplane. So this is A transpose X equal to 0, and you can easily say that this set C, where is for this hyperplane, where is the upper half space? Upper half space, it is along the normal. So that's why it is in this part. This is the upper half space H plus. I'm calling it A. Call this direction right now A1. So A1 up H plus of A1. A1 transpose X equal to 0. Okay, this is the hyperplane. Call it give notation in order to visualize everything, especially in a very clear way. So this is the hyperplane. Okay, so we can observe that C is always in the upper half space. That means it simply says that if you take any element from C and do dot product with X, what would be dot product? Product would be non-negative. That means it would be greater than equal to 0. It satisfies. So simply we can say that A1 belongs to dual cone. Dual cone of the given set C. Similarly, if you take another direction like this way, if you're taking, call it A2, then with respect to A2, by considering A2 as a normal vector, define a hyperplane. So if you consider this one A2, so what would be normal uh, hyperplane? It would be this is the hyperplane. Picture might be clear to everyone. If you anyone having any issue with visualization of this one, then just inform me. So this definitely you are considering A2 as a normal, and you are defining another hyperplane H2. HA2. So what is equation of HA2? So you will call it A2 transpose X equal to 0. Okay. Now you just see what you see. Where is C? C is again. So where is the upper half space of this hyperplane? It is again uh, this portion. So again we observe that C is here. Where is C? C is in upper half space of A2. HA2. Upper half space is coming. So we can further say that here if you take any vector from C, any element from C, and it do dot product with A2, then again we will observe that dot product is what? Non-negative. It is greater than equal to 0. So very fine. That means A2 is again in the, where it is? It is in the dual column of the given set C. Greater than 0. So you will call it A2 is in the dual column. So now your question would be that what is the extreme direction of the dual cone? So, so similar wise, if you take this, what is this one? Uh, what kind of direction this one? If you take this one as a direction, and if you define uh, a hyperplane by considering this direction as a normal vector, then you will get the corresponding hyperplane would be this. That means the extreme direction of the given set C, it just lies on the this direction, on the hyperplane. So what would be name of this one? So I would like to give name of this one, because here D1 it just lies on the hyperplane whose normal vector is this one. So I will give name of this one related to D1. So I will call this normal vector D1 star, because again here the corresponding hyperplane, this hyperplane, it is again defining a hyperplane in such a way C is coming in the positive half space. That that means H D1 star. C is coming in H1 D star plus. So that's way call it and the corresponding hyperplane call this is the hyperplane. So call it H D1. Okay, but remember that if you take any direction vector here, suppose this one you take, call it Z. I am giving changing the notation. I am not taking it A no more. So here, if you take Z and with respect to Z by considering as a normal vector, and if you define a hyperplane, then you will observe this kind of hyperplane you will get. This is the hyperplane with respect to Z. So that means Hz would be what? Uh, Z transpose x equal to 0, and here clearly you can observe that it is not doing it. This Hz is not doing a separation, clear separation. That means some element of these elements or these points of C are in the upper part of this hyperplane, and these much portion are coming in lower half space, in the lower half space of with respect to Hz. So simply we can say that Hz is not doing a clear separation. So we can say that Hz is not a del direction, or simply we can say that Hz doesn't belongs to, it is not in the dual cone. So what is the extreme direction of dual cone? It is one extreme direction is D1 star. That one is perpendicular to the extreme direction of the given set D, given set C. That means perpendicular to D1. And similarly, you will get another extreme direction of the dual cone would be what? This one would be. And this one is what? From the geometry, it is very much clear. And explanation is similar. D2 is D2 star. D2 star is perpendicular to second extreme direction of the given set C. So you observe this much of cone. So this cone is a dual cone of the given set C. This blue shaded set. So blue shaded set is the given set, and you can easily say that blue shaded set, it is not a convex set, it is a non-convex set. But the corresponding dual cone C star, the orange is shaded, you can see that this one is a convex cone. Even more than that, it is also containing boundary point. So you can say that C star is a closed convex set, closed convex cone. It is having a cone structure, so you can say that dual cone is always happens to be a closed convex set. So this is the concept of duality. If you apply duality twice, then you will get back your set itself. And that concept is true only the case when your C happens to be a convex. Otherwise, it is not true in general. So here I have already mentioned that. So dual cone is a closed convex cone. So this is the idea of duality with respect to a set, how to construct a dual cone. Now another kind of dual cone is that we are calling it a polar cone, and these are very much needed. I have already mentioned that even during that convex set part as well, because whenever you are going to apply optimality condition, what you do, you always have to find a polar cone and dual cone. Dual cone is nothing, just it is a direction cone from optimality point of view, and polar cone is nothing, just it is a normal cone. So that a practical example also I would recall. So here we are again taking a any kind of set C in the Euclidean space Rn, then how we can define polar cone? So polar cone, we are saying it is a collection of all the direction in such a way the given set it is no, it is in the negative half space. Remember that for the dual cone, the given set was in the positive half space with respect to that direction, but here in case of polar cone, just reverse is happening. The given set should be in the negative half space. That is the criteria. That means less than equal to 0. Dot product of any direction from the normal cone or polar cone must be less than equal to 0. So that is the criteria. So in another sense, you can say that polar cone happens to be negative of dual cone. Just play with replace here in the definition, replace a by minus a, and what will happen? Then this less than equal to condition, it will be changed into greater than, and negative sign will come out. So what it is, just definition of what? So the previous definition of dual cone, and negative sign is coming, so that's why negative of dual cone. So polar cone, simply you, from the definition it signifies that it is negative of dual cone. So there is a very interesting relation between these two. Both can exist together. And so again we can see that the polar cone, it is again a closed convex cone, and it can be seen that polar cone is equal to the negative of the dual cone. So that relation I had already discussed. Now I have taken here one example. The same set I have already taken. So again, what you do here, take any given set, see whether it is convex or no, or not convex. Then what you do, algorithm is again find extreme direction of the given set. This one is the first extreme direction d1, and this one is second extreme direction d1. You may ask a question why I'm calling this one first extreme and second, because in sign geometry always we counterclockwise rotation, always we consider positive things. So that's why we move in counterclockwise representation. That's why I'm calling it d1, and this one is d2. Now what you do in order to construct polar cone, so what you do, uh, all the processes are similar whatever I discussed with dual cone. That means find all the possible direction in such a way c would be in negative hyperspace, not in positive hyperspace, it would be in negative hyperspace. In that process all the uh, process is similar, just I am trying to draw it here extreme direction of the polar cone. So what is the one extreme direction would be this one, this call it d1, d1 naught, d1 naught, d1 naught is the notation for polar cone, because a star has been already reserved for dual cone. So that's why d1 naught we are taking it here. So d1 naught is just perpendicular to first extreme direction in negative way. That means so it was the d1 star, d1 star was this one perpendicular to d1. In such a way we had constructed d1 star in such a way that c is coming in the positive hyperspace of the uh, hyperplane with respect to d1 star. So d1 not is nothing, just it is negative of d1 star. So, also it is here in the definition of dual cone and polar cone, you can see that so d1 not is nothing, just it is what negative of d1 star. So again what you do, find the dual cone and then take a negative of all the possible direction, then easily you will get your polar cone. And what is this direction, this d2 naught, d2 naught is nothing, just it is what negative of d2 star. So what is d2 star, this is the d2 star which is perpendicular to the extreme direction of c and d2. So this is the d2 star is perpendicular to t2. So you can say that, so all these things are geometrically very much related and geometrically very much clear. So all these are dual concept. You must remember that all these are dual concept, duality with respect to shape. So anyhow, whenever we study duality, all these things we need to recall it. Okay, so polar cone is already I have already described. If you have any question, then let me know and ask. Otherwise I'm going to discuss one more uh, part of these two in directly in the perspective of optimal point. Now what we do, we are just trying to define dual cone and polar cone with respect to optimal point. In last case we had taken reference point was origin. Now here our reference point would be what, our reference point would be optimal point. If you are coming to define uh, dual cone and polar cone with respect to optimal point and feasible set. So here this x is feasible set of the given optimization problem. So definitely where will be hmm, optimum point, optimum point there definitely it would be on the boundary. So this x is the optimum point of the optimization problem in this feasible set. So we are considering a feasible set X in Euclidean space Rn, and definitely we consider that this feasible set is a non-empty because we need a solution at least. So that's why we are taking non-empty feasible set. If it is empty, then we simply will call that optimization problem is an infeasible problem. So we don't look for that. Okay. So what would be the polar cone of this? Polar cone of this can be defined as uh, uh, before going to define polar cone, we are defining here one is this one, we are calling it direction cone. Call this one direction cone. So these things we had already discussed, and closure of direction cone, it happens to be uh, dual cone or tangent cone of the given feasible set. We call it direction cone. So direction cone is what? It is the collection of all possible direction in such a way. If you just proceed in that direction by epsilon a step from the optimal point x bar, then you are not just leaving that feasible set. You remain in the feasible set. That means these are the possible direction. These are the possible direction. If you proceed in this direction A, just by some epsilon step size, then you are not leaving this feasible set, you remain in the feasible set. That's why in that process we are getting a direction cone. Now once we are having a direction cone, then we can talk about tangent cone. So what is tangent cone? It is the closure of all tangent cone. That means easily you can, what you do, how you can get tangent cone. So draw the tangent to the feasible set at x, that optimal point. So this tangent at the feasible set, it will give your extreme direction of tangent cone. So this one, call it d1 star. So here your tangent cone is nothing, just it is a dual cone of your feasible set, and this one is d2 star. Okay. This, so directly, no, sorry, here feasible, you have already got your feasible or another name of direction cone, you can say that it is a feasible direction also. F word I have taken it here, feasible, uh, from the feasible word, so you can say that it is a feasible direction cone. And what is tangent cone? Tangent cone is just what you do, draw that extreme direction of this feasible set. So it will give your tangent cone. And what you do after that, you define extreme direction. Okay, then if you consider extreme direction and construct a cone, then you are getting a tangent cone. Now what you do next, define your uh, dual cone of tangent, uh, tangent cone. This easily you can define like this way, draw perpendicular to d1. Perpendicular to d1 would be what? Call it d1 star. Perpendicular to d2 is what? D2 star. So in that process, what you are getting? So you are getting this cone is what? You call this cone is dual cone of, I'm giving a name it here. Call it, or simply you can call it notation I have taken T star. T T star. That means dual cone of X. Okay. And what is this? You can observe that this normal cone, how you can define normal cone is just what? Negative of your tangent cone. So here you can define it like this way. So normal cone, directly you can define it like this way, negative of tangent cone at point, optimal point x, with respect to the given feasible set x. Okay. So this is the normal cone is negative of tangent cone. So that relation you have already get. So normal cone is all, where would be normal cone? Normal cone, it would be inside the polar cone of this uh, feasible set. So normal cone is inside in the polar cone of the uh, feasible. So polar cone we denote it by x naught. And what we say tangent cone. Where is tangent cone? tangent cone, it is inside the dual cone of feasible set. So tangent cone is inside the, it is a proper subset of uh, dual cone of the feasible set. So that is the criteria. You can observe it all this. So from the graph, everything is already clear. So again, normal cone and tangent cone all uh, are getting all are related with dual cone as well. So now coming to conjugate function. So conjugate function, how we had defined. So here, if we are having a function from Rn to R, and then how we define f star from Rn to R, then conjugate function also it would be a function from Rn to R. So what we do, we take any direction y, then define a hyperplane y transpose x, okay, and subtract fx from this hyperplane y transpose x, and we try to maximize the gap between y transpose x and fx, and that value it will define conjugate function when we maximize. So when we maximize, so that means we are maximizing with respect to x, the gap between y transpose x and fx, and simply we say that the maximum gap between y transpose x and fx, that is defining your conjugate function. And it is the domain of conjugate function, it consists of uh, every direction y. Remember that it is n dimensional vector, but I am calling it direction intensely because direction many time I have already discussed. So it is actually a vector, but consider from the direction perspective for better understanding. So for which this supremum is finite number. So that means this supremum is defined. So we are that will so it is collection of all the direction for which this supremum is defined. That collection will define the domain of this conjugate function. One geometry you can see it here. I will talk about geometry as well. So here geometry is coming like the here for function of one variable. For that clear geometry, I am talking about function of one variable. So here you have taken, if your function of one variable, then y transpose x would be what? It would be just y into x, because y is also a scalar, x is also a scalar. So it will just take the form of y times x or x times y, because inner product is what? It is commutative in nature. Okay. So like you can observe that this is the plot of uh, y transpose x, and this is plot of fx. Fx is clearly, it is non-convex in nature here, but when we will find a conjugate function, conjugate function will be always a convex function. So that is the beauty of finding conjugate function. So what you do, try to in try to shift the given linear function in the direction of what, uh, keep on shifting in the direction of y, parallel to y, is the direction parallel to y, in such a way the gap would be maximum between. So where you so you keep on shifting, so you can shift up to this point in such a way this linear function y transpose x, it is touching this function. So here at this point you can observe that what is the, if you observe the gap between y transpose x and fx. So here what is the gap between fx and fx here? Fx and y transpose x, 0. If you come here, what is the gap? Gap is this vertical bar. If you are coming here, what is the gap between function and this? If you are coming here, what is the gap? It is this. And if you are coming here, this is the maximum gap. You can observe that this is the maximum gap. So that's way here we are getting a value of conjugate function with respect to that direction. This is the value of conjugate function. So you can simply uh, see this criteria of defining conjugate function. I have taken few example. So if you consider a linear function x plus b or affine function, so then as a function of x, so we have to define conjugate function. To define conjugate function, first we will define y transpose x, and we subtract fx from this function, and that's why we are getting y transpose x minus a ax minus b, and what we it is a linear function. So if you are having a linear function, we can't apply calculus technique to get the optimal point, or to, because it is again defining conjugate function is just dealing with finding supremum or infimum, or supremum or maximum. So that's why we simply can't apply calculus technique, because it is a linear method. So we can just go for general concept of finding supremum of linear function. That means we have to look into corresponding coefficient. So the coefficient of the linear term. So what are the linear term here we are having? So here linear, this is the linear term, this is the linear term, and minus p is constant term, so it won't affect much in the process of optimization. So we take x common, and we'll keep other things coefficient of x in the bracket. So here y y will come minus uh, a transpose. I'm writing in linear function, general linear function form. So that's why y transpose will come. And I had already mentioned that transpose is a dual operator. So if you apply it twice, it will vanish. It will give original one. So y minus a transpose times take whole transpose times x minus b. This function you can write it like this way. This function you can write it like this way. This linear function. So y transpose x minus ax minus b. So tell me when this function would be bounded. Now it is a linear function complete. So when this function would be bounded, anyone would you like to answer when this function would be bounded? It is a linear function. Anyone willing to answer? Nitin, when a linear function is bounded. Okay, Sujit, would you like to answer? Sujit, are you there or not? Not present. Aditi, anyone is present or all are absent? Okay, then reply. I'm asking that when that function is linear function is bounded. I've written a linear function there. Y minus a transpose uh, halt. I have already see it here. Simply come to see here. So I'm talking about this function. When this function would be bounded, I have taken y minus a transpose to the whole transpose times x minus b. When this function would be bounded, y, yeah. So it is already written here. You should answer that time. Okay, so here I should define linear function like a transpose x. So automatically it will come like this way. Okay, fine. Then nice answer. You are getting it. When this function would be bounded when the coefficient of linear term is zero. If coefficient of linear term is zero, because if this coefficient is non-zero, then you are getting a linear function. What is nature of linear function? It is unbounded below as well as unbounded above. It is unbounded if you are having a linear function. But if you make the coefficient zero, then the linear term will vanish. It will not present here. This coefficient is zero, and only remaining term would be minus b. Minus b is a fixed number, so that's why you are getting a bounded function. So being a boundedness condition, what criteria we are putting? Y equal to a. So nice, that is the answer. Okay, so we got the criteria of bounded function. So what would be conjugate function? So due to that, the conjugate function of this given linear function would be what? A transpose x plus b. It would be just minus b. This is the conjugate function. It is coming. So conjugate function of a linear function is a what? It is a constant function. Now, if you come to find conjugate function of negative log, so what is the conjugate function of negative log? So it is not a linear function. So definitely you have to look to see the boundedness of this one. And here, what you do, you can apply calculus technique. That means you are willing to find maximum value of this function y transpose x plus log x. negative negative cancel out, that's a plus we are getting it here. So how can you find maximum? So find the gradient of this function, call it another name g, call it g. Find the gradient of g. What will be gradient of g here? You gradient, that means gradient you are finding with respect to x. So gradient of g would be what? Simply it would be y. This one is linear term. So you, if you differentiate with respect to x, you will get y. And what is the derivative of, suppose it is function of one variable. So what is the derivative of log x? What is the derivative of log x? 1 by x. Yeah, fine. So directly you are getting derivative of this function, linear function plus log x. It is just y plus 1x, and equate to 0 in order to get the optimal value. So if you equate to 0, then what you are getting? Your direction y is coming what? It is just coming negative of 1 by x. And substitute back this y equal to 1 by x here, and you will get your, or x equal to 1 by y, you will get your what? Conjugate function. So that's way your conjugate function here, it would be what? Write it here, space issue is here. So f star y, it would be put substitute back x equal to negative of minus or negative of 1 by y, x equal to y. So your conjugate function, it would be in the term of y. So here substitute back. So product, it would be product of x and y is what? Now it is 1. Product is 1, and here you take log of negative negative log plus log of minus 1 by y. Okay. And when logarithmic function is defined, logarithmic function is always defined for positive real number. So minus 1 by a you are taking it here. So that's where you have to put a condition here that a must be negative, then minus 1 by y would be positive. So that's where here this is the domain of the conjugate function of this given function, minus negative of log x. So this is the domain, that means a negative real number, and this is your conjugate function. So everything is already written in here. You can observe that. So this is the idea to find conjugate function of a given function. Now I'm coming to discuss about Lagrange duality. It is more important to discuss in order to solve an optimization problem in much easier way. So just I think today we will introduce only Lagrangian, and in next class I will discuss Lagrange duality in detail, because we don't have much time. Just around 5 minutes we are having. So how we can define Lagrangian for a given optimization problem? So consider an optimization problem that it is a general optimization problem. It is written as we need, that means we have to minimize a objective function f of naught subject to inequality constant. This one is a standard inequality constant. Always we take inequality constant less than equal to 0. Okay, and this one is equality constant. So this one is general optimization problem. I'm not saying that it is a convex optimization problem. I had already mentioned that duality is the concept which convert any kind of optimization problem into a convex optimization problem. So that's way I have taken this kind of a standard form under a certain condition. So here x is we are calling it decision variable coming from Rn. D is the domain of the problem, and P star we are calling it optimal value of this optimization problem. Then we can define a new function Lagrangian, which is defined from this triplet Rn to Rn cross Rm cross Rp. So Rn is coming with respect to decision variable. Rm is coming with respect to what? This variable it will be associated with inequality constant. That means there we will introduce a new term, new variable lambda, that we will call it Lagrange multiplier with respect to inequality constant. And Rp here, in Rp with respect to, in Rp what we do, we will introduce a another Lagrange multiplier with respect to this inequality constant. Okay, So that's where all these are coming. So here this lambda we will call it dual variable, and mu generally we won't call this dual variable because it is unconstant in nature, and dual variable it is constant in nature, because lambda it will always take value greater than that, it would be component wise greater than equal to 0, component wise greater than equal to 0. So we are defining Lagrangian as a weighted sum of objective function plus infinity constant plus equality constant. So here lambda I and mu I all are Lagrange multiplier. Lambda I is associated. Remember that lambda I is associated with infinity constant. Mu I is associated with equality constant. So easily you can see that here there is no role of sign here. Why? Because hi of x is equal to 0. If you multiply any quantity with 0, that will vanish, that will again become 0. So that's why the mu is unrestricted. So every mu I can be negative or positive or 0, whatever is. So there is no specific condition over mu I. So simply every mu I is just a real number. You can say it can be any real number, any type of real number. We are not putting any condition. Okay, so it is unconstant kind of variable, Lagrange multiplier we are saying. Now, if we come to see lambda I is what kind of uh, nature it will have. So we are multiplying this lambda I with infinity constant. So what we do? So how here we are having less than equal to infinity constant, and if we take negative lambda, then it will change the inequality. So that's why we are not allowed to take negative value of lambda I. What we have to take, lambda I must be greater than equal to 0. Each lambda I must be greater than equal to 0. So that's why we are putting a positive condition over lambda I, and lambda I is a later we will call it, when we will go to Kaketi condition, that time we will call lambda I happens to be a dual variable, and mu I is unconstant dual variable, and lambda I happens to be constant dual variable. So those are the things. In actual, these are just Lagrange multiplier. So this is the concept of defining Lagrangian of a given optimization problem. Regarding attendance, go and mark your attendance there in Google Classroom. And in further, if you have any doubt, you can ask